Okay, so we are starting the final exam review. So what we're going to do is I'm going to pose a question, okay? And then when I pose that question, if you're watching live, then I'll give you some time to think about that and come up with an answer as an individual. And if we all have agreement on the answer, then we can just move to the next question. And and then in the next question, maybe there's some disagreement in the answers that people selected. And so we'll have a discussion. So if you're watching on YouTube, you want to pause after each question so we don't reveal the answer. If it's live, I'll give time to answer individually and then possibly a group discussion where we try to convince the other person who has a different answer than we do that we are correct, they are incorrect. Okay, so that's the idea. We really want to focus on our reasoning and our logic as to why we chose that answer. So obviously some people will select some answers they're not confident in, right? And so then there's an opportunity for somebody to help you, to help explain to you how they got their answer and help you learn. Okay, so let's go ahead and I'm going to pause the recording just to get the next question up, and then I'll read out the question. Okay, so we begin in chapter 21, which was the first chapter that we started with at the beginning of the semester. This is the chapter on electric charge and electric fields. Here is the first question. So X and Y, as you can see in the figure, those are two uncharged metal spheres on insulating stands and are in contact with each other. A positively charged rod R is brought close to X as shown in figure A. So if we're looking at figure A here, this figure right here, either X and Y are in contact and this rod R, which is positively charged, is brought close. Okay, now sphere Y is moved away from X, as in figure B. Here's figure B. And the question is, what are the final charge states of X and Y? The options are both X and Y are neutral, X is positive and Y is neutral, X is neutral and Y is positive, or X is negative and Y is positive, and then finally both X and Y are negative. So if you're watching on YouTube, again, pause the video now and we'll be back quick with the answer and discussion, but everybody who's here live is going to have a chance to think and then maybe discuss with partners. So we'll be back in a flash. Okay, so after our discussion here, we are all in agreement now that the answer, or the answer that we've agreed to, is answer D. So let's think about it now. So when we bring a positively charged rod, like this one here, close to the sphere X, what happens is we draw a little bit of negative charge towards that positively charged rod. And when negative charge is moved towards the rod, it leaves behind some positive charge, right? In fact, it leaves behind the exact same amount of positive charge. And so because of this, what we call polarization, when we move sphere Y far away and no longer in contact with the sphere X, what happens is that extra charge, that extra negative charge that kind of came over onto the X sphere is now trapped there. It cannot get back over to the Y sphere. And actually, this figure B here is a slightly misleading. Once we move the sphere Y away, what actually happens is the charge begins to kind of evenly distribute itself around the sphere now, if we move the rod R away. So now we ultimately end up with two charged spheres. This is called charging by induction. Notice that the rod R never made contact with either of the two spheres. So we would call this charging by induction. Okay. You can kind of, now that we understand Faraday's law, like induced voltages, induced magnetic fields and things, those are all happening without contact, right? So that's what the word induced means. So to finally kill the suspense here, indeed, D is the correct answer. So good job on that one. We had a weird distribution of, or not a weird, like a kind of a uniform distribution of answers to start. And then after discussion, we all kind of came to agreement on answer D. That's good. Okay, so let's go to the next question. We'll do one more question out of chapter 21. We're going to try and hit 2 questions per chapter, and then with extra time, we can go back and revisit some other topics. So here I have a question ready already. I just need to get it in here. So let's paste it in here like so. And it's okay that we didn't pause the recording in this case because it comes up pretty quick. So here is the second question. We have 2 large, flat, horizontally oriented plates that are parallel to each other, a distance d apart. Halfway between the 2 plates, the electric field has magnitude E. If the separation of the plates is reduced to d over 2, what is the magnitude of the electric field halfway between the plates? Our options here are 4 times E, 2 times E, 1 times E, 0, or E over 2. Okay, so I'll give you a minute to think about that. If you're watching the recording on YouTube, I'm going to pause the recording now. So we're going to be back with the answer and discussion in the blink of an eye. So make sure you pause the video now and try the question yourself. And we're back, and it seems like we had a good amount of disagreement before and after the discussion. So the choices that that we have here after discussion are between these two here. So majority actually thinks it's 4E, and the minority thinks that it's E, and it's kind of split between just those two. So let's talk about it. So the first thing that we should do is we should draw ourselves a picture. So to get a picture here, we have these 2 parallel plates, and they're flat, they're horizontally oriented, and they're parallel. And there's a distance d between them. And it tells us that there's some kind of electric field here. I'll draw it in the downward direction. So maybe this plate is positive and this one is negative. And then it says, at this middle point right here, it says if we decrease the distance to d over 2, in other words, we make the plates closer together, then how would that change the electric field at that same point? So I'll just draw it in there. And now the distance here is d over 2. So the way to think about this question is to remember that when we have 2 parallel charged plates, again, the top plate is positive, the bottom plate is negative. Nothing about that changes. We have this nice uniform electric field between the plates. So the magnitude is the charge density over epsilon naught. And does the charge density change if we decrease the distance between the 2 plates? No, the plates still have the same amount of charge as they had before we changed their distance. So in this case, sigma, which is the charge density, doesn't change. So there's no change in sigma, and therefore there is no change in the magnitude of the electric field. So to finally put an end to the suspense, those of you who chose C have the correct answer. All right, so we'll be back with the next question in just a moment. All right, we're back with the next question. This is a long one, so hopefully it'll stimulate a lot of discussion. We're going into chapter 22 now. So our first question out of chapter 22, which is entirely focused on Gauss's law. If you remember, Gauss's law was a nice, easy way of getting electric fields when we have a lot of symmetry. But if we don't have a lot of symmetry, it becomes really difficult to use Gauss's law. In any case, this is the question. Which of the following statements about Gauss's law are correct? There may be more than one correct choice. There may be more than one correct choice. Okay, and so the statements are as follows. A, Gauss's law is valid only for symmetric charge distributions such as spheres and cylinders. B, if there is no charge inside of a Gaussian surface, the electric field must be zero at points of that surface. C, only charge enclosed within a Gaussian surface can produce an electric field at points on that surface. D, if a Gaussian surface is completely inside an electrostatic conductor, the electric field must always be zero at all points on that surface. E, the electric flux passing through a Gaussian surface depends only on the amount of charge inside that surface, not on its size or shape. Okay, so I'll give you some time to think about that. If you're watching on YouTube, pause the video now and take some time to think about each of these statements and determine which of these statements, if any of them, are correct. And we're back. We had a good amount of discussion there on a lot of these different points. Some of the choices that people are going for here. We have some people for B, option B here. So this statement. We have some people, a decent number of people for option C. D looks fairly common, and E looks fairly common. I mean, and there's even one person thinks A is correct, or no, he changed his answer. So nobody thinks A is correct, okay? So we're still pretty split on this one. I would say a lot of people have chosen D, or D is the most common. Okay, so let's talk about each of the statements. Gauss's law is valid only for symmetric charge distributions, such as spheres and cylinders. Well, I can give a counterexample to that right away. I can put a point charge here, and I can put a point charge here, and I can draw a Gaussian surface like this around these 2 point charges. And the electric flux between those on that surface, the electric flux through that surface is dependent upon the sum of these 2 charges. So if this one is plus Q and this one is minus Q, the net electric flux would be 0. And this is a situation where the charge distribution is not cylindrically symmetric or spherically symmetric. In fact, there is some symmetry here for this charge distribution, the dipole charge distribution here. There's a little bit of symmetry there. So let's go ahead and make it less symmetric. Let's make this one plus 1/2 Q, and we'll put another little Q over here, and this one is a 1/2 Q. Now it's completely asymmetric. There's no symmetry here in this problem. But the electric flux is still 0. So A is not true. Gauss's law is a law, right? It's one of Maxwell's equations, in fact, as we've seen already. So Maxwell's equations are valid always, right? All right, B. If there is no charge inside of a Gaussian surface, the electric field must be 0 at points on that surface. Well, that's not true. Take a look at this dipole again, right? We have a plus Q and a minus Q. We draw a Gaussian surface around these two charges. You have to think about this as a three-dimensional surface, so it's coming out of the screen and it's going back behind the screen as well. The net flux there is zero, but the electric field is not zero. The net flux is zero, but the electric field is not zero. For example, if I were to draw the surface really, really close to the positive charge and really, really close to the negative charge like that, then the electric field here would be very big at the surface, in that direction there for the positive charge, and in that direction there for the negative charge. Because we're so close to that positive charge, right? The electric field there would be K Q over R squared in magnitude, in both of those cases. Whereas somewhere up over here at this point, the electric field would be a little bit less in magnitude. So the electric field must be zero at points on that surface. That is not true. So A is not true, B is not true. Option C, only charge enclosed within a Gaussian surface can produce an electric field at points on that surface. Only charge enclosed within a Gaussian surface can produce an electric field at points on that surface. Well, again, we can take a look at a positive charge here, negative charge here, and we can look at a Gaussian surface which encloses just this negative charge here. But of course, we know that the electric field lines of the dipole look something like this, right? And so at this point right here on the surface, the electric field is the sum of the contribution from the positive charge outside of the surface and the negative charge inside of the surface. We would never use Gauss's law to figure out what the electric field is for a dipole, because Gauss's law just requires a little bit of symmetry to use practically. It still applies when there is no symmetry, but it is not practical to use when there's not enough symmetry. So we want to make sure that we have these concepts in our mind when doing problems with Gauss's law, because sometimes it could be a choice. You could have the option of using Gauss's law or the option of maybe using an integral with Coulomb's law, something like that, right? So you want to make sure you can pick the easiest option. So there you go. There's a Gaussian surface where the electric field at points on the surface are due to charges outside of the surface. Remember, Gauss's law is a statement about the flux through a surface. The flux through a surface, not a statement about the electric field. You can use it to calculate the electric field in some cases. Okay, so option C is not correct. Let's take a look at D. If a Gaussian surface is completely inside an electrostatic conductor, the electric field must always be zero at all points on that surface. So if we have an electrostatic conductor, I hope that we remember that the electric field is always zero. So the electric field is always zero inside an electrostatic conductor. So therefore, if we have a Gaussian surface which is completely inside of an electrostatic conductor, then of course the electric field will always be zero on all points on that surface. So this statement is correct. This statement is correct. Option E, the electric flux passing through a Gaussian surface depends only on the amount of charge inside that surface, not on its size or shape. So maybe at this point we would want to write down Gauss's law. So this side of Gauss's law is the electric flux side, E dot dA. I did hear one group talking about this E dot dA integral here. And on the right-hand side of Gauss's law, we have the charge enclosed in the surface divided by epsilon naught. So what goes into Gauss's law? You have the flux, which is on the left, and on the right, you have the charge inside divided by a constant. So there's only two things in Gauss's law. There's the flux, and there's the charge inside the surface you're calculating the flux on. So this is a true statement. The flux only depends on the amount of charge inside the surface. It does not depend on the size or the shape. Now, calculating the flux, the integral on the left-hand side might be challenging if you have an oddly shaped surface. But Gauss's law tells you you can calculate the flux by simply counting the number of charges and adding them up. So you don't have to do the complicated integral on the left-hand side if you know how much charge is inside that surface. Okay, so E is a true statement as well. So the correct answers here are D and E. So that was probably a tough question, huh? All right, so I'll go ahead and pause the recording now, and we'll be back in a moment with the next question. I'm going to give everyone a chance to ask me questions who's here with us live. Okay, so we're back with the next question, our second Gauss's law question here. The question is, an infinitely long non-conducting cylinder of radius 2 centimeters carries a uniform volume charge density of mu, I wrote mu, but I think I should have wrote rho here. So let's change that to a rho. So that's a volumetric charge density of 18 microcoulombs per meter cubed. Calculate the electric field at distance r equals 1 centimeter from the axis of the cylinder. So if the cylinder is 2 centimeters, and we're looking at the electric field a distance 1 centimeter from the center, and that means we're inside of that non-conducting cylinder, right? Our options here, 2.5 times 10 to the 3 Newton per Coulomb. So these should all be 10 to the 3 here. They should all be 10 to the 3 Newton per Coulomb. 5.1 times 10 to the 3 Newton per Coulomb, 0. 2 times 10 to the third, and 10.2 times 10 to the third. So looks like either the answer is 0 or it's something roughly of order of magnitude 10 to the third, right? So now, since we're doing a calculation question, I'll ask you guys to provide any formulas you might want. I'll give you any formula that you want to be able to do this question here. So can anybody want to speak up? Or you can write in the chat. Okay, I'll help you out a little bit. We're in the Gauss's law chapter, right? So let's write Gauss's law. Excuse me. Can anybody think of any other formula here that might be useful?
Volume of cylinder.
Volume of a cylinder. So the volume of the cylinder is the area of the cap times the height or the length of the cylinder. So that would be pi r squared times the height. Anybody think of any other formula we might need for this one? How about the surface area of the body of the cylinder, right? How about the surface area of the body of the cylinder? So let's say surface area. Well, that's the two areas of the caps, right? So it would be 2 pi r squared plus the area of the body, which is 2 pi r times the height of the cylinder. Okay, so this is the total surface area of the cylinder. That, not all of that might be relevant for this question. We've seen problems like that before, right? So with that being said, I'm going to leave it up to you guys now to figure out how to do this question. Okay, so we're going to pause the recording. Those of you who are watching on YouTube, now you need to pause the video, and we'll be back shortly with our explanation. Okay, so we're back, and we have a unanimous answer, and that is answer E here. So let's quickly go through the question here. So infinitely long non-conducting cylinder of radius 2 centimeters carries a uniform volume charge density of 18 microcoulombs per meter cubed. Calculate the electric field at distance r equals 1 centimeter from the axis of the cylinder. Let's go ahead and try and color code things a little bit here. So if this is our cylinder right here, like this, we need a Gaussian surface inside of this thing here. I don't know why I drew a solid line there. But this is our Gaussian surface here. And since this thing is positively charged and it's an infinitely long non-conducting cylinder, we have symmetry here, right? So the electric field can only be going out this way, or this way, or out of the page at us, right? And into the page away from us. So the angle between the electric field and the surface element is always going to be 0. In other words, the electric field is perpendicular to the surface. Remember, the area element vector always points perpendicular to the surface. Okay? So our E dot dA part of Gauss's law here becomes E times A, and it's area of the body of the cylinder, just the body of the cylinder. No electric field is going in or out of the caps of the cylinder, so we should not count that area. The electric field penetrating that surface there is 0. So those terms drop out of our expression on the left-hand side of Gauss's law. So E times the area of the body of the cylinder has to be equal to charge enclosed over epsilon naught. To figure out how much charge is enclosed in this surface, we need to know the charge density. So it has a charge density rho of 18 microcoulombs per meter cubed. So we need the volume of the cylinder. So I think it was Duke who said we would need that. So that's good, Duke. What we need to do now is recognize that the density is constant, so we do not need to do an integral. We can simply do rho times the volume. Okay. If we do rho times the volume here and plug in some of this stuff, the volume of the cylinder may be pi big R squared times h, but the volume of the Gaussian surface that we've chosen is pi little r squared times h. So 1 over epsilon naught rho pi little r squared times h. We can take h to be the height of this thing. Of course, it's infinitely long, so we're going to want to cancel h on both sides in the end. Area of the body of the cylinder is h times the area of the cap. Sorry, the circumference of the cap. So it's 2 pi little r times h. So we equate these two. Pi little r squared h, and we do indeed see that the little h's cancel here. And in fact, 1 power of r and the pi's also cancel. And what we end up with here for our answer for the electric field, our analytical solution, is rho r over 2 epsilon naught. And we see that it is linear with respect to r. That is common behavior for uniformly charged volumes, that as you increase the size of your Gaussian surface, the electric field is increasing linearly with the radius. Okay, because you're enclosing more and more charge, right? Okay, so if we were to plug in the numbers here, we do indeed, and I'll save you the trouble here. I'm not going to plug in the numbers. We'll just save some time here. You do indeed see that the answer is going to be E here, 10.2 times 10 to the third newtons per coulomb, round to the appropriate number of sig figs, which is 3. I think in the problem, the original problem statement, they said 18.0 there. So yeah. All right, so we'll be back with the next question here shortly. All right, so our next question is beginning our chapter 23 review. So we have a metallic sphere of radius 5 centimeters is charged such that the potential of its surface is 100 volts relative to infinity. Which of the following plots correctly shows the potential as a function of distance from the center of the sphere? So remember, chapter 23 is all about potential, electric potential difference and electric potential energy and electrical work, things like that. So we'll be back shortly with the answer and discussion. So if you're watching on YouTube, pause the video now and give this one a shot. Okay, so we're back after a good amount of discussion for this question here. Metallic sphere of radius 5 centimeters is charged such that way the potential of its surface is 100 volts relative to infinity. Which of the following plots correctly shows the potential as a function of distance from the center of the sphere? We have unanimous consent here on this plot here, which would be plot X, answer B here. The potential on the surface of a sphere is 100 volts, and of course it must decrease as kq over r, similar to a point charge because it is a sphere, and spheres have spherical symmetry, point charges have spherical symmetry. So the potential should fall off as 1 over r, proportional to 1 over r. And so as we get twice as far away from the center of the sphere, then the potential should decrease by a factor of 2, right? So this definitely encapsulates that, since the potential at 10 centimeters from the center is at 50 volts, okay? So another possibility here was this plot right here, but notice that this plot here is decreasing proportional to 1 over r squared here, right? And so that one couldn't be the case, but certainly it looks very similar to plot X there, right? So plot W and plot X look similar, but X is the correct choice there, answer B. All right, so we'll be back with the next question shortly, which will also be in chapter 23. And we're back with the next question, another which statements are true type of question. So I thought there was a lot of good discussion when we did this one earlier. So which statements are true for an electron moving in the direction of an electric field? There may be more than one correct choice. So answer A, its electric potential energy increases as it goes from high to low potential. Answer B, its electric potential energy decreases as it goes from high to low potential. Answer C, its potential energy increases as its kinetic energy decreases. Answer D, its kinetic energy decreases as it moves in the direction of the electric field. And answer E, its kinetic energy increases as it moves in the direction of the electric field. So I'll give you some time to think about that. So if you're watching on YouTube, again, pause the video now, try to evaluate whether each of these statements is true or false. And for your answer, you want to select all of the true statements. So if you think A, B, and C are true, select A, B, and C. Okay, we'll be back shortly. All right, we're back with this question here. So most people went with either A, C, and D, or they went with B, C, or D. So B and D certainly were the most common answer there, C and D. And then it seems like there's still a little bit of disagreement on A and B. So let's take a look at this one. Which statements are true for an electron moving in the direction of an electric field? There may be more than one correct choice. Its electric potential energy increases as it goes from high to low potential. Excuse me. All right, so let's think about this. So electric potential energy increases as it goes from high to low potential. Let's maybe think about, I saw one group kind of discussing in this way. They're thinking kind of about the parallel plate capacitor here, where we have a positive plate here and a negative plate over here. I kind of like this way of thinking about it. So when you have these two plates like this, the electric field here is in this direction from positive to negative. And the positive plate is at high potential and the negative plate is at low potential. So maybe we can write over here, this is high potential, and this is low potential here. So which statements are true for an electron moving in the direction of an electric field? So it's moving in the same direction as the electric field here. So if this is my charge, let's say the charge is here, it has velocity in this direction like this, because it's moving in the same direction as the electric field. Okay. So again, let's recall, what are we trying to show here? We're looking at answer A. Its electric potential energy increases as it goes from high to low potential. Electric potential energy increases as it goes from high to low potential. Okay, so the electron here, is its potential energy increasing? Well, the electron has a force on it, because it's a charged particle, equal to minus E times the electric field. And notice that there is this minus sign here, which means that the force on the electron is in the opposite direction of the electric field. So there's a force on it in this direction. So I would say that its potential energy is increasing as it moves against the force that's acting on it, right? That's kind of like lifting a mass against a gravitational field, right? So gravitational field is downwards like this, and we're going to lift this mass up so that it ends up here, right? And the force in this case is down, and we're moving this mass against that force. So we're increasing its potential energy. Same situation is going on here. We're moving the electron in a direction against the force that's acting on it. So that means we're doing work on it to move it against the force, right? And then if we let it go, it has all this potential energy. So it's going to accelerate back to high potential. So A is true. A is a true statement here. So some key takeaways here. How do we analyze this statement? The way we analyze this statement is if we want to do away with the picture and everything and just get really down to the fine details, we need to think about the direction of the force on the electron and whether the electron is moving in the same direction as the force or the opposite direction of the force. And we also need to remember that if the electric field is pointing, let's say, from left to right, as we've drawn it here, then that means the potential difference is increasing to the left, opposite of the electric field. So we have to remember how to get the direction of the force And we have to remember where is high and low potential. Electric field always points from high to low. All right, so that automatically rules out B, right? B can't be correct because A is correct, right? So these two statements are like the duals of one another. They're opposite statements here. Okay, so let's go to C now. So a lot of people liked C. Its potential energy increases as its kinetic energy decreases. So this statement of potential energy increasing, so kinetic energy decreases, certainly that's going to be true, provided we can show that the potential energy is increasing, right? As long as we can show that for this electron, potential energy is increasing, then we know its kinetic energy is decreasing. We've already shown that. We've already demonstrated that the electron is moving against the force that's acting on it. And so it must have an increasing potential energy, and therefore its kinetic energy is also going to be decreasing because there's a force on it against the direction of motion, right? So it's slowing down, so its kinetic energy is decreasing. So C is certainly true. C is true. Let's box that one. How about statement D? A lot of agreement on statement D as well. Its kinetic energy decreases as it moves in the direction of the electric field. Its kinetic energy decreases as it moves in the direction of the electric field. So again, if an electron is moving in the same direction as the electric field, well, that means that it's moving against the force on it, right? So if it's moving against the force on it, then it must be slowing down, right? If it's slowing down, its kinetic energy decreases. So D is also true here. Oops. Okay, and then how about E? Nobody went for E, which is a little bit surprising. Its kinetic energy increases as it moves in the direction of the electric field. Okay, well now I can see why no one chose E. The kinetic energy is decreasing as it moves in the direction of the electric field. So this one is not correct here. Interesting how some of you were choosing between A and B, but not choosing between D and E. That's kind of interesting. It seems like everybody got C, right? So that's good. Okay, so I'll go ahead and pause the recording until we're ready for the next question, and I'll let you guys ask me any questions. Okay, so let's get on to chapter 24 now, which is a chapter all about capacitance, excuse me, and dielectrics. So here we have a question. The four identical capacitors in the circuit shown in the figure are initially uncharged. Let the charges on the capacitors be Q1, Q2, Q3, and Q4, and the potential differences across them be V1, V2, V3, and V4. So don't get confused by the wording there. They're all initially uncharged. Okay, but we're going to label their charges Q1, 2, 3, and 4, and their voltages V1, 2, 3, and 4. The switch is thrown first to position A and kept there for a long time. It is then thrown to position B. Which of the following conditions is true with the switch in position B? Okay, so it's thrown to A, so it's to the left on your screen. So that capacitor C1 is connected to the voltage source V0. And then the switch is thrown to B. So capacitor C1 is disconnected from the voltage source V0, and then it is connected with the other capacitors, C2, C3, and C4. Okay, so our options here are, and again, the question is, which of the following conditions is true with the switch in position B? So V1 equals V2 equals V3 equals V4, V1 equals V0, V1 plus V2 plus V3 plus V4 equals V0, Q1 equals 3 times Q2, or finally Q1 equals Q2. So which of those, which of the following conditions is true? Okay, so I'll give you some time to think about that. If you're watching on YouTube, go ahead and pause the video and try this one yourself. I did get a good question here in the direct message. So you do want to assume that the switch is thrown to position B and you have waited a long time. So which of the following conditions is true with the switch in position B after a long time has passed? Okay, so after a long time has passed. So thank you for that question. A long time has passed. Okay, so pause the video if you're watching on YouTube. Try this one yourself. We'll be back shortly with the answer and discussion here. All right, so we're back after quite a bit of discussion here. The only conclusion we've come to is that no one knows the correct answer to this question. Let me just start by giving you the correct answer. So the correct answer here is A. A is the correct answer. Let's try and understand why. We have two circuits in this problem. Okay, we're told that the switch is thrown to A for a long time, which means that the circuit we're dealing with here is this circuit here. We have a capacitor with capacitance C1 and a voltage source with volts V0 here. That means that this capacitor gets charged up after a long time to some charge. Let's just call it Q here. Okay. When capacitor C1 has that maximum amount of charge, it's fully charged up to Q, the switch is thrown to the other side over to point B. So the switch is thrown. What that means is now our circuit is simply 4 capacitors connected in series here. Okay, so when we have 4 capacitors connected in series like this, and one of them has an initial amount of charge. So this one now has an initial amount of charge Q here. What's going to happen is that charge is going to distribute itself amongst the other capacitors. If this capacitor has a charge Q on it, then that means it has a voltage on it, right? And the voltage on that capacitor is going to start a current flow in this circuit here. And as the current flows, it's going to begin to charge up these other capacitors, and eventually the voltage on these other capacitors, of course, is increasing, and it's increasing against the voltage of this other capacitor here. And so eventually the current flow is going to stop, right? After a long time in any circuit where we have a capacitor, after a long time, the current is going to stop flowing eventually, right? When the capacitor is fully charged. That applies for DC current, okay? If we have AC current, then it's not the same. Capacitor will charge and discharge, charge and discharge. So how does this work when E is synonymous with A due to Q equals C? I'm not sure I understand your question, but let me continue on with my explanation because I have not explained why A is the answer yet. So what happens here is we have essentially a capacitor which is supplying voltage in this second circuit here. And these other capacitors, there's no voltage on any of their plates. So to understand this question, we can actually apply Gauss's law. If we apply Gauss's law, we can determine that any 2 capacitors in series, so now I'm going to draw another diagram which is a little bit easier for me to apply Gauss's law to. So suppose we have 2 capacitors in series here. We can always apply Gauss's law to this middle region here where the 2 capacitor plates are connected. The net charge in this Gaussian surface here is 0. to start. You can imagine that this surface is perhaps these two capacitors right here, right? So the Gaussian surface here is between these two capacitors. So initially that's neutral, right? These guys aren't charged up, so they're just neutral. They have no net charge. So if they get charged up, what has to happen is that, let's say this plate becomes negative, it picks up a negative charge, then the exact opposite charge must be picked up by the other plate in order to conserve charge. So this is charge conservation here. So you may remember that we actually made this argument in class when we discussed series capacitors. We made this exact argument here. Charge has to be conserved for this branch because remember, between capacitors, no current can flow, right? If you have two plates like this and there's a vacuum or a dielectric, no current flows from one plate to the other plate, right? So we certainly have to have the charge on one plate of one capacitor opposite to the plate on the other capacitor because of this wire that connects them. Okay, and so when that happens, of course, that region, charge has to be conserved. Of course, charge has to be conserved in the other region as well, right? So if I were to draw, let's say, a purple Gaussian surface here, which went all the way around the circuit, right? Blah, 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 all the way around the circuit, and then comes back over here like this, right? Then charge also has to be conserved here. So if this plate picks up positive charge like this, then this plate has to pick up negative charge like that. Okay, and we can extend this argument to any number of capacitors connected in series. Okay, so if I draw this Gaussian surface here in orange, I can draw this one here, right? I can draw that surface. I can draw this surface here, right? And I can draw this surface here, right? And I could even draw some slightly more elaborate surfaces to show that even the plates on opposite ends have to be the same. So if I draw a surface like this as well, right? I can draw that red surface. I can draw this black surface as well on this side. And I can draw all possible Gaussian surfaces. And I can make the same charge conservation argument over and over and over again and show that the charge on all of the plates for capacitors connected in series has to be the same. So what happens to this charge Q? The charge Q is distributed. It's distributed to the other capacitors. We have 4 identical capacitors, and so the charge is cut by 1/4. So each one of these capacitors stores Q over 4 charge, and that's what we would label the Q1, the Q2, the Q3, and the Q4. Would be this Q divided by 4, and they would all be the same. Another way perhaps to see this without making these charge conservation arguments is to see that we do indeed have 4 capacitors connected in series. And so the equivalent capacitance here would be C over 4. If we wanted to replace that with a single capacitor, it would be, they would all be in, I guess maybe actually this is not a great argument. Probably you want to combine 3 of them actually. You probably want to combine 3 of them. Combine 3 of them, so you have a you have a C1, equals C, and then you have a CEQ for the other 3 is C over 3. And then I think you can show that because of the difference here in the capacitance of the 2 capacitor circuit with C1 and a CEQ, you can again show that the charge will distribute itself evenly amongst those capacitors. That would require a little bit more work though on your part to do that. You have to assume that you start with an amount of charge Q, and then you have to go and figure out how Q distributes itself amongst those 2 capacitors. and then from there you can figure it out. And I think you have to do a little bit more work to do that way than this argument with charge conservation. Okay, so I hope that argument was clear. It's all coming from charge conservation. You have to do all of the Gaussian surfaces and show charge is conserved, and the charges on the various plates has to be the same for all possible combinations of Gaussian surfaces here. And then it's clear that A is the correct answer, because if all the charges are the same, then the voltages have to be the same, right? Because we have identical capacitors. So Q equals C times V. Okay. Any questions about that? I'll let the people here who are here live ask me questions as you are watching at home. We're a little bit over the allotted time. Of course, the video is short for you guys because we've paused the video, but I think maybe if people want to stick around, we can do one more question from chapter 24 before we end it. Okay, so I'll see you in a minute. Okay, so we're back, and actually I made a mistake in this question, so we want to correct that mistake. So good job for catching me in that mistake. Let's go ahead and explain what was wrong with what we did before here. So look at the top right here. This is where I'm going to start the explanation here. So the correct answer is answer D here. Let me go ahead and box it again in blue to emphasize the answer is D. That Q1 will be equal to 3 times Q2. So what we want to do is we want to think about the capacitor here, C1, as beginning initially with some charge Q and a potential difference V1 on its plates, and then combine the other capacitors into a CEQ over here on the right-hand side. And CEQ, just using our standard capacitor rules here on the right, CEQ is just the inverse of 1 over C2 plus 1 over C3 plus 1 over C4. That's going to come out to C over 3. Remember, we have 4 identical capacitors in this question, so each one has a capacitance C. Excuse me. So we'll label that CEQ with a CEQ, and we'll say it has a voltage on its plates VEQ. And also something that we've noticed but we haven't shown yet, and we're going to show that, is that what's going to happen is charge is going to stop flowing as soon as the voltage on capacitor V1 is equal to VEQ. And so in red, by the circuit diagram here, so let me highlight that in red up here, we will be able to show that the charge on capacitor 1 will decrease to 3/4 Q, and the charge on the other 3 capacitors will increase to 1/4 Q. And since those capacitors are connected in series by the same Gaussian surface arguments before in charge conservation, we know that the series capacitors will all have the same charge. So 1/4 Q is going to be the charge Q2, Q3, and Q4. So you can see, 3/4 Q is 3 times 1/4 Q, right? So the answer here will be D. So let's see how that works. Just a quick note here, charge stops flowing when V1 equals VEQ. But VEQ, what is that? Well, it's V2 plus V3 plus V4. Okay, that's VEQ. So like we said, when V1 equals VEQ, charge will stop flowing. So we start with that. That's our starting place. So right here is our starting place. Once V1 equals VEQ, there's no potential difference, so no charge will flow. Well, we have our capacitor equations here. So for V1, that's going to be equal to Q1 over C1. And for VEQ, that's going to be equal to QEQ over CEQ. Okay, and what is CEQ? What do I mean by that? Well, what is QEQ? What do I mean by that? It's the same as Q2 and Q3 and Q4 because capacitors in series, again, they share the same charge. They all have the same charge. We can replace the C1 and the CEQ in terms of C. We have 4 identical capacitors, so we can just say C1 is C, and then CEQ is going to be C over 3. Replace QEQ with C, because as you can see here, right, series capacitors, again, QEQ is equal to Q2. So we'll replace that right there, circling it in red. And what we find is because the capacitance decreased by a factor of 3, that 3 flips up and multiplies there, the Q2. So Q1 is equal to 3 Q2. And the total amount of charge that we started with, so this answers our question now, so the answer is D. The total amount of charge that we started with was Q. So if after a long time that charge decreases to Q1, and that charge distributes to the other 3 capacitors, then the only way that that can happen is if Q goes to 3/4 Q, the 3/4 of the initial charge, and the others go from 0 to 1/4 of Q. So that has to happen all in proportion. So the total amount of charge that we began with, which was Q, remains the same. Okay, so I'll go ahead and pause the recording, and we'll be back with one more question. Recording. Okay, we're back. So last question here for chapter 24. An ideal air-filled parallel plate capacitor has round plates and carries a fixed amount of equal but opposite charge on its plates. All the geometric properties of the capacitor, the plate diameter, the plate separation, are now doubled. If the original energy density between the plates was U0, what is the new energy density? So what equations might be relevant for tackling this question before we jump right into it? Because I will give formulas on the final, right? So can anybody think of any useful formulas that we might want to tackle this question here?
The formula of energy density.
So energy density, we can write as 1/2 epsilon naught E squared, the electric field squared. Any other formulas? How about maybe capacitance of a parallel plate capacitor? Anybody remember that? Let me help you out a little bit. There's an epsilon naught, there's an A, and there's a D. Is it A over D? Is it A times D? Is it D over A?
A over D.
A over D. So if the parallel plates are have more area, they store more charge, right? And then if they're spaced further apart, then they store they'll end up storing less charge. The capacitance will be lower. V equals E times D. Sure, we can put that one here as well. I think that's enough to solve this question. If you want to use more formulas, though, that's probably okay, but might be a bad sign. So go ahead and try this one if you're watching on YouTube. Go ahead and try this one yourself, and we'll be back with the answer and the discussion. Okay, we're back, and now we're going to discuss this question here. So everyone seems to be in agreement that the answer is E, that the energy density will decrease by a factor of 16. So let's see if we can work that out here. So a couple things to note: the plate diameter doubling. If the diameter doubles, then the area increases by a factor of 4. You can see that from the following expression. The area of a disk is pi d squared over 4. So if I increase d by a factor of 2, I pick up a factor of 4 because d is squared here. If you're not familiar with this formula for the area of a disk, you know that the diameter is twice the radius, right? So if you double the diameter, that means that the radius should double as well. Okay, so if the area increases by a factor of 4, and the plate separation increases by a factor of 2, then that means our capacitance will look something like this: 4 times the area over twice the distance. So the capacitance is going to increase by a factor of 2. Okay. what's going to happen to some of these other parameters here? So for example, the equation here, if the distance between the plates doubles, then the voltage here would double because the electric field between the plates, parallel plates of equal and opposite charge, would remain constant, right? So the voltage would go to twice the voltage, but the electric field here would remain the same. Let's see, anything else that changes here? I don't think so. So now we kind of need to piece everything together, right? So what we need to do now is we need to figure out how the energy density is going to change. Excuse me, I think I said the electric field does not change, but the electric field changes. Excuse me. The electric field changes. Otherwise, we wouldn't have a change in U here. So actually, yeah, forget what I just said here. Oops, not true. Okay, so what do we want to do here? So one way we could do this is we could say that, let's see, actually, what is the most efficient way to do this question? Why doesn't somebody else share their method for doing this question? Why don't we do it that way? Why doesn't somebody else share their method? Since I didn't think about it while I was listening to your guys' discussion. Anybody want to share their method?
Capacitance with the electric field.
Capacitance, say it again.
I think we needed like a formula to manipulate with E.
A formula to manipulate E. Is that what you said?
Yeah.
Okay,
But
so
it relates to capacitance.
okay, so what formula?
I thought it would be something like E equals Q over C, but I could be wrong.
V equals Q over C. Okay, I thought you said E. So V equals Q over C. Good. Yeah, this will work. Okay. And then what?
Make them equal to each other?
Make.
I don't know. I really don't know.
No, this is good. No, this is good. Be confident. This is correct. So make these two equal, right?
Right.
So ED equals Q over C. And then what?
Now we have 2C substitute in.
So we have 2C. We can substitute that in.
Right.
So this is going to go to Q over 2C now.
So that means that E is half.
E goes.
Or is doubled. I don't know.
Okay, what about this term though? What about this term?
Is that going to be doubled now too, Rich?
Yes.
Now...
Yes, exactly. So that one's going to double now too. So a 2D here. So E times 2D is going to be equal to Q over 2C. And then what?
That's as far as I can go. My brain's fried.
Okay, so divide the 2D over now, right? Divide the 2D over. So if we divide the 2D over, we get E equals Q over 4CD. If nothing doubled, we would have E equals Q over CD, right?
So now we have E. E should be 1/4.
1/4, exactly. So E, so this implies, so double arrow there. This implies that E goes to E over 4. Okay, so E goes to E over 4, which means here, if we plug in a quarter E, what factor do we pick up in the denominator?
16.
A 1/16th, right? So we're going to pick up 1/16th. So the U is going to go to 1/16th U, and the answer here is E. Very good. Okay, so that completes the final exam review. We went like an hour and a half over, but I think the video on YouTube is not going to be that long at all because we kind of paused and cut out a lot of the discussion. So even those of you who attended live, go back and go through the questions and try them again and make sure that you've learned from them, and then maybe listen to the explanations again as well. Okay, so we're going to end there. So bye, YouTube.